Hi everyone, my name is Weiji, and I'll just be presenting some of the work I did over the course of my PhD in collaboration with my PhD supervisor, Horgan, who's based at the Antarctic Research Center in Wellington, New Zealand. So the topic is how we can sort of resolve the bad topography of Antarctica using a super-resolution generative adversarial network. So I'd like to start with...
Sorry, Weijin, this is Marco. If you could speak louder, you come a little bit softer on your voice.
Sorry. So let me see what's... Hello, is this better?
Yes, thanks.
Okay, cool. Yeah, so moving on to my second slide. So I'd like to start with a motivation. Why do we need high resolution images of the Antarctica bed? So as Richard, Ali, and some of the other speakers have talked just now about, this is really just to better inform like ice sheet models, because with bed topography, ice slides over rock or sediment, and depending on how rough that bed is, ice typically would have a hard time sliding over rough beds compared to smooth beds, and also having like a higher resolution bed topography can help with things like subglacial hydrology. So my background is actually in remote sensing. I work on mapping subglacial lakes, and just having like a 1K resolution BedMap 2 isn't like sufficient for some tasks. So if we can get like a higher spatial resolution, that would sort of help with quite a few downstream tasks like mapping subglacial things, and this all of this leads into sort of the sea level rise equation. So we having a high resolution bed helps us to sort of see decide like how fast ice can move and how much like sea level rise we should be planning for in the future. So the big question is, how do we get a better bed map? There are sort of two main approaches. The first approach is a direct approach, and that's to go out on plains or skidoos and then use this thing called an ice penetrating radar, where you can capture how the bed looks like using radar signals. So this is a slightly outdated map of some of the spatial coverage we have over with ice penetrating radar surveys. So this is captured by people like from BAS, the Chinese teams and the American teams. So lots of work that went into this. And but as you can see, these are mostly clustered around the spatially clustered around the coastal areas or around like field stations. So there are like missing parts in some data gaps in quite a few parts of Antarctica. So to fill in these gaps, what people have used is an inverse modeling approach as well. Oops, sorry, was I muted the whole time?
No, sorry, I accidentally muted.
Oh, okay. Right. Okay, cool. Yeah, so there's also the inverse modeling approach, which is to take ice surface observations, so things like elevation or ice velocity, and then invert for that using like a Fourier model. So this is something that you might be familiar with Bed Machine Antarctica, which does this sort of inverse modeling approach. The work I'm presenting today, the DeepBedMap GAN model, this uses convolutional neural networks instead. So it's a bit experimental, but also quite an exciting approach in a sense. And these two methods they're quite complementary methods. So you can sort of combine those in the future. So the key idea is how can we like sort of incorporate the sparse ground truth data we have over like geographically distinct regions with the ice penetrating radar, right? And also combine that with the satellite data we have, which is practically over the whole continent of Antarctica, except for the pole hole, of course. So we can train this like function mapping. How about we train like a function mapping between the ice surface observations and the ground truth in the areas where you have them, so the ground truth areas. So once we train this function mapping, we can then sort of apply this train model. So using the same ice surface observations, apply the same train model, and then produce high resolution beds where there's few or little survey data. So this is sort of the key idea with that. But with this function mapping is actually, because it's an inverse model, or an inversing, it's quite hard, quite a hard task. So removing data is quite easy. You just have to like right click, and then delete, press delete, right? But going from a low resolution input, so increasing data, so going from low resolution to high resolution images, this is one of those tricky problems. And so super resolution in computer vision, it's been around for I think since the 1980s, but it's only been in like recent the past decade or so with convolutional neural networks that things have gotten actually like looking quite promising. I won't go into the long history of super resolution, but just to give you a flavor, over probably like the past 5 years or so, one thing that people are moving towards are this thing called generative adversarial networks, started by Ian Goodfellow's classical GAN paper, I think in 2014, if I'm not mistaken. So you've heard about GANs before, but this is sort of, so I'll go through this quickly, but the idea of a GAN is instead of having like a standard convolutional neural network produce a single mean squared error-based solution, so this blue box in the middle, which is quite smooth looking. So this is pictures of, I think, a fur of some animal. Instead of having this smoothed out approach appearance, so you can have like a high peak signal noise ratio or a high PSNR value. But with again, what we actually want is to get those like texture. So the texture, in this case, is of like the animal, but we can also imagine like if you want the texture or of topography, then we would again is one way to sort of reconstruct that sort of natural looking images. And the intuition behind this, an analogy like most people like to use is with GANs is there are two competing networks. So you have like an artist or a generator model that generates some images. At first it looks like maybe just like cartoons, and which isn't good, but you also have like a second network, which is like the teacher or the discriminator model. And that teacher has knowledge of what real dogs look like. So it can sort of, the teacher can feed back that to the artist or the generator model. And then there's like a cycle going on where eventually we hope that with the teacher's guidance, the artist or the generator model can generate more realistic looking images, in this case of dogs, but it can also be like, the topography of Antarctica. So this is just to show you one of the architectures. This is from Ledig et al., the SR GAN model, which is one of the first super resolution GAN models. So you have the low resolution input on the left, and essentially with the generator network, you just pass it through a sequence of convolutional layers, and towards the end you have some upsampling layers, more convolutional layers, and you get, in this case, a 4 times upsample super resolution image. And then the network on the bottom, the discriminator network, that is that takes in the super resolution result, and you also pass it in images which are actually real, and then this is just a standard VGG network. And what the discriminator needs to do is decide whether the images that are passed in are real or fake, and this knowledge is sort of passed back into the generator network through an adversarial loss function. So these have like parallels with the actor-critic models in reinforcement learning, if any of you are more familiar with that. And so fast forward 1 to 2 years later, we have an enhanced version of this. So they've sort of the same group, they've improved the model a bit. One key thing they found was if you remove the batch normalization layers, that actually helps with the super resolution result. And they've also tweaked sort of the upsampling regime as well, and added like more skip connection, so denser networks that can sort of learn more features. Right, and one more thing, because so what I talked to you about just now is just like single image super resolution. You're taking one single image and then producing a single super resolution result. But because we're blessed with geographical data from lots of satellites, we can actually add additional context to help improve our super resolution results. And an useful analogy I like to think is with classical like pan sharpening in remote sensing. So say given like a 15-meter panchromatic Landsat image and a 30-meter resolution Landsat RGB image, if you combine the two using a pan sharpening technique, you can get like a 15-meter RGB image. So this has been done before using classical remote sensing techniques, but recently there are actually like GANs that can do that now. So for example, this PS GAN by Liu et al. So this is something where we can combine, not just use our low resolution input, but also combine like better contextual data to sort of conditional model to do better. Right. Yeah, so to bring it all together, this is how the generator model looks like. So on the left, we have our low resolution BedMap 2 input on the top here. That's at 1K resolution. We also feed it in the REMA ice surface elevation model at 100-meter resolution. Measures ice flow velocity. It's 450 meters, but I've resampled it to 500 meters. And also Antarctic snow accumulation to get that sort of DHDT ice surface elevation change factor. So that goes through a series of convolutional layers. I concat the inputs, so they're a consistent tensor size, and then that goes through this core sort of module, lots of like residual connections, and towards the end we have like a few nearest neighbor in blue, nearest neighbor upsampling, followed by convolutional layers and some deformable convolutions to get this final DEM of a so 4 times upsampled version of BedMap 2 essentially. Oh, and this was built using trainer, which is another defined by run scheme similar to PyTorch. And these are sort of the results to look at. So on the very left, you have DeepBedMap's DEM. So this is over Pine Island Glacier, by the way, the main trunk. So you can see with DeepBedMap, we have these, we cover these like fine sort of rough texture patterns compared to BedMap 2 on the second from the right, from the left, which is quite smooth. And if you take A minus B, you get C here, which is sort of, you can see the difference map where we're recovering lots of those rough texture patterns. And just for comparison, here's BedMachine, which actually does like a pretty good job already, but it's inherently it's still quite like a smooth surface compared to what we can produce with a GAN model. Okay, and just to get
up to wrap up in 1 minute.
Okay, cool. Yeah, just to show how the model looks like when it's training. We have so it starts with at epoch 1 it doesn't know much, but as we progress in training, it's picking up. Okay, so there's like a hill here, and then by epoch 100, we can see it's recovering like quite a few like the subglacial topography features. This is over Toots Glacier. I'll probably skip through this or go through it real fast. So essentially with DeepBedMap in purple, we can recover like higher roughness values which is similar to the ground truth compared to BedMachine. So you can read more in the paper. And and because GANs are tricky to train, we also use this Bayesian hyperparameter the tuning approach. So instead of doing like a random search or a grid search, we sort of focus our hyperparameters at the areas where it matters. And yeah, so all of this takes about 1 to 2 days to train, and but just like 1 minute to run on the test log B100 once it's trained. So it's pretty decent actually. So this is my last slide. To conclude, what's next? What's next for this sort of work? So we still need better data. So high resolution data is always welcome. From those ice penetrating radar campaigns, I know COVID has put a lot of gotcha things into plans into this array, but we're still hoping to get more of that. And I've been waiting for BedMap 3 for probably the past 4 years. Apparently it's coming out this year, but they've been saying that for the past 3 years or so. Hoping to see that come eventually. And then for the remote sensing people, we need to fill in some data gaps. Mostly due to cloud cover, but you know, we're pretty onto that. And for the machine learning people, we can sort of upgrade different pieces, new architecture designs. I'm looking at maybe like physics-informed neural networks, or also different architectures like transformer models, or even doing some neural architecture search to find out what's a good architecture to use. And maybe, yeah, we can combine the DeepBedMap with things more like physics-informed models like BedMachine to produce the next version of this. Yeah, so the slides are here and the paper is here. GitHub repo, everything's open source right from the start, so I'll put this in the chat. If you have any questions, I'm happy to take them now.
Yeah, thank you so much. And we can have questions in the chat, so we can go to the next speaker.
Recording stopped.
I really liked your results. I think, especially scaling the GANs up, that's very challenging. So cool work.
Yeah, it's quite a lot of effort to train.